Okay. This is really not meant to be the entire leveling lecture. I'm really just going to try to use this time to go through some of the main concepts from leveling. And hopefully if you all have any questions about any of this material, you'll type in some questions or raise your hand, which you can do with some of the buttons there, and we'll address them as we go. So some of the slides we'll be skipping through. These are the same slides that are available on Blackboard, so you do have access to all of this material. When we start to talk about leveling, it's really important that we look at the terms that are used in leveling. If we don't all understand the verbiage and the lingo that's being used, it makes it very difficult to come up with appropriate data and complete leveling loops. So leveling is really about determining the elevation of points, or essentially the differences in elevation between points. When we talk about elevation, we're talking about the vertical distance above or below a very specific datum. The datum that most of you are probably familiar with is mean sea level. So when you're driving up in the mountains and you see those road signs that say, elevation 1,400 feet, elevation 3,200 feet, that's what we're referring to. And typically those road signs are based off of mean sea level. I'm going to skip some of the rest of these to move forward. Okay, so visually, this is what we're talking about when we talk about a level line, a level surface, taking an elevation. Let's see here. See if I can get this to work for me. Change the color to kind of a yellow color. That'll work. Okay, so you can see here, I'm hoping you can see that that's the ground surface. And what we are looking for is this difference in elevation between points A and B. Not seeing. Okay, now you're seeing it? Okay. All right. So off of our datum right there, which we're using as mean sea level, here's our level line, right? Oh, here's our level line here, our datum of mean sea level. So we're measuring perpendicular here and perpendicular here. The difference between those 2 points is the difference in elevation between those 2 points. So if you have the elevation of A, you can determine the elevation of B by determining the difference between them. And we'll see how that works as we go through. Okay, some other general terms of vertical datum. Any level surface to which elevations are referenced. Typically, we assign that surface an elevation of 0. Just makes it easier, which means you can actually have a negative elevation. There are occasions when you are actually surveying in, let's say, an underground pipeline where your elevations may actually be negative because the ground surface above the pipeline may be your 0 elevation, and now you're actually below that elevation mark. Vertical control and benchmarks, these are incredibly important. Benchmarks are a relatively permanent object. They're not very often natural anymore. In the history of surveying, they were occasionally natural items, trees, rocks, things like that. Now they are typically brass. The video that goes along with this material that's on the OER, there are some pictures of some of the benchmark items that are in use now. At any rate, a benchmark is essentially a permanent object, as permanent as we can get it to be, having a marked point where we know what that elevation is above or below whatever datum it is that we're using to create that benchmark. And it's a permanent mark. So it's a mark that surveyors can go back to at a different date and time and have as a starting point. because we know what that given mark is, what it represents. Vertical control is a series of these marks or other points of known elevation that have been established within a basic area, also called basic control or level control. So basically, very often if you're working on, for example, a construction site, you may have to go through that construction site several times to lay grade, to check building heights, curbs, gutters, to lay all of these items out and then verify that they're in the correct location, both horizontally and vertically. So you would set up a benchmark off-site or just off-site, and you would set up some control marks within the site so that you could continue to verify these locational points on the site without having to keep redoing all of your work every single time. Datums. There are a lot of different datums out there. As we talked about, mean sea level is the one that most of us are aware of, most familiar with. And that was the traditional datum that was used. In North America, 19 years of observations at tidal stations in 26 locations on the Atlantic, the Pacific, and the Gulf of Mexico shorelines were reduced and adjusted to provide the National Geodetic vertical datum of 1929. So basically they said, you know what, this mean sea level is great, but how do we actually determine what mean sea level is for the United States, right? I mean, it's an awfully big place with a whole lot of different coastlines, different oceans, the whole bit. So in 1929, they established NGVD, the National Geodetic Vertical Datum of 29. It is related to mean sea level because they used various tidal stations to create the datum, but it is not technically mean sea level. In 1978, the National Geodetic Survey began a general readjustment of all of these leveling points that they set up across the country, right? I mean, the Earth is in physical motion at all times, and earthquakes change things, tides change things, people change things, right? So in the late 70s, they said, we need to go back and make an adjustment on all of these permanent marks and these permanent measurements. The adjustment was supposed to be completed in 1988. So it was called NAVD 88. However, it wasn't actually finished until 1991. This new datum, NAVD 88, was tied to one representative tidal gauge benchmark located in the St. Lawrence River Valley in Quebec, Canada. The point is known as Father Point. So basically, instead of looking at multiple tidal gauges across the Pacific, the Gulf, and the Atlantic, it was determined that they would use a single gauge at one location in Quebec, Canada as the datum for NAVD 88. That's important because when you go back and look through various surveying documents, and when you look at the lab data information for the leveling lab, you're going to see that much of the published benchmark data is actually reported as either NAVD 29 or NAVD 88. So the same exact point in the same exact location will actually have two different sets of numbers associated with it, depending upon whether you're looking at the 1929 datum or the 1988 datum. Other definitions: a temporary benchmark. It serves the same purpose as a benchmark, but it's not a permanent mark, and it may not have been established with the same level of accuracy as you would need to establish a permanent benchmark. A turning point is a point that we use to temporarily transfer an elevation. You're going to see in a moment that in order to take elevation measurements, you need to have a line of sight, and if you don't have the line of sight you need to create a temporary point or a turning point in order to get to your next mark, and you just carry the elevation with you. So here's what this looks like for a single setup. Okay. So we have our direction of survey. That's important. It doesn't matter which direction you head, but once you head in a direction, you must continue in that direction. So it's important to know which way you're going. So our direction of survey on this slide is from the right to the left. Therefore, we know, oh, there we go. We know this is our benchmark A, and it has a given elevation at this point, right? It's given. It was set by someone else who set all of these control points. We know what it is. We're going to hold our rod on our point. We're going to set up our instrument approximately halfway between our 2 points, and we're going to take what's called a back sight on our point of known elevation. Our back sight, by definition, is a rod reading taken on a point of known elevation to establish the elevation of the instrument's line of sight. So if this point here, right there at the bottom of the rod, is 410.26 feet, and we took a measurement of 4.71 feet on the rod, we know what the height of this line is, the center line of the instrument. We call that HI, height of instrument. Notice it's a capital HI. A small hi is also the height of an instrument, but it means something different, so they should not be confused. Height of instrument, capital HI, is the elevation of the line of sight through the level. It's calculated by taking the elevation of the benchmark, 410.26, and adding the reading on the rod, or your back sight, 4.71, which is how we're getting 400 right here, 414.97 feet. Now, any reading that you take off of this instrument, off of this line of sight, this dashed line here, any direction that you point this instrument, you know that the height of that instrument is 414.97. So to get the elevation of B, which is what we're trying to establish because that's our direction of survey, we go ahead and take what's called a foresight, or an FS, a foresight, a minus sight, several different names for it, a foresight, on our rod located at that point. In this example, the foresight reading on the rod is 2.80 feet. So what would that make the elevation here at B? Oh, trying here. My writing isn't working so well. Elevation of B is going to be equal to Josh, you can't hear? I feel a little bit like the Verizon commercial. Can you hear me now? Okay, the captioner can still hear me. Josh, I'm not sure why you can't hear me. Oh. Okay, so we're back in business. Okay, so Gracia, Josh, or Michelle, what would be the elevation of point B? If we know that the height of our instrument is 414.97 and our foresight shot is 2.80, what would that make our elevation of B? Okay, Michelle typed in with 412.17. Josh and Gracia, do you agree with that? Hello, Josh. Yeah, okay. Okay, right. It is 412.17, and we got that by subtracting 2.80 from the height of our instrument. So we know so basically what we're doing is we know an elevation here, we're going up to here, we're going across this way, and then we're coming back down here to the measurement at B. This is the same single setup that we were just looking at, but tied back to our original diagram that showed leveling lines in the ground surface. And as you can see here, the numbers are different, but it's the same setup. Your setup is that with your level, you're creating a 90-degree angle between the horizontal line of the level, your instrument, and the vertical line here to here. There's your 90-degree angle between your instrument and your vertical line down towards the center of the earth. So when you hold your rod here and take a back sight, and then turn and take your foresight, if that's our direction of survey, then the difference between those two readings is the difference in elevation between those 2 points. So we can see here that our elevation at A over here is 61.27 feet, plus the 6.27 gives us the HI, the capital HI, the height of the instrument, the horizontal line of sight. Okay, what is going on there? And then if we were to subtract the rod reading over here, we would then have our elevation here at point B. And this is what we will be doing in lab a week from today. So the steps to doing this, simply put, first you must level the instrument. We spent quite a bit of time during the last lab practicing how to level the instrument. You're going to take a plus sight or a back sight on your known point. That back sight is the reading on the rod. You then compute the height of your instrument. You turn your telescope to bring the rod at point X into view, which is your forward sight. Your rod reading is the minus sight or foresight on that particular point. And then you calculate the elevation of that point using your foresight shot, your rod reading. And then you repeat, and you do it over and over until you complete your entire leveling loop. When taking your measurements, let me back up just a little bit here. When taking your measurements between your 2 points, you want to make sure that your instrument is located approximately in the middle of the 2 points, or as close to the middle of the 2 points as you can possibly get it. Why would we want that? What benefit would that be? Any guesses why we'd want to be doing that? Best results, distribution of error. You're both correct, but the answer I'm looking for is distribution of error. If your instrument is set up here, and this is the center line of your instrument, right? That's taking a reading as best as I can draw it with this tablet and this pen. There we go. If by chance your line through your instrument is just ever so slightly off, and I'm going to exaggerate it here so that we can see it. Let's say it reads just a little bit low. When you turn that instrument to take the reading on the other side, it will read low as well. And remember that we're looking for the difference between the 2 points. So if the instrument is set up in the middle, the amount of error that you're off here, this distance here, again greatly exaggerated, compared to the amount of error that you're off here is going to be the same and will cancel itself out because you're equidistant from both. So again, we're looking for the difference. The difference will still be the difference that it should be, even though our instrument is a little bit off. If we were to be reading a rod extremely close, we would not have such a great error here, and we would have a much larger error here, and then our error would not actually cancel out. So you want, on every possible opportunity, to make sure that your instrument is located approximately, as best you can, between the 2 points in which you're reading. Okay, let's talk a little bit briefly about curvature and refraction. In case you all hadn't noticed, the Earth isn't really flat. So if you are taking a measurement over an extremely long distance, you must account for the curvature of the Earth and refraction of light coming through the atmosphere. So if you look at this diagram here, this would be our horizontal line of sight as we're taking our measurement. The farther away you go, here's our 90-degree angle, so here's where our instrument is set up. The farther away we go looking for our rod, the more the curvature of the Earth is pulling away from our horizontal line, giving us this error here, the amount by which a level line and a horizontal line diverge over some specified distance. Okay? We have to account for that in our calculations if we are going to measure over a great distance. The error, though, is very small and essentially negligible for distances under 1,000 feet. At 1,000 feet, this error, this divergence here, is 0.024 feet. Okay? So basically you're looking at 2/100th of a foot. That's not so bad. But anything greater than 1,000 feet, and you're looking at a much greater divergence, and then we need to accommodate for that. At 300 feet, the divergence is only 2/1000. So at 300 feet, our error would be equal to 0.002 feet. So you can see that that's completely negligible. When you look at the effects of refraction, they operate opposite the effects of divergence or curvature. So I know this is a little bit difficult to see here, but this whole distance here is the effect of curvature, but this smaller distance up here is the effect of refraction. So basically, you can take the combined effects of curvature and refraction. So basically the error due to curvature and the error due to refraction. And they've been combined into a single formula to account for both of those errors, especially since they work against one another. So you can see the formulas here. So curvature, the error due to curvature and refraction in meters is equal to 0.0675 times k squared. It's very important that k be in kilometers. In this case, if you're looking for the error in feet, 0.574 k squared, k must be in miles. And in this option, if you're looking for it in feet, 0.02064 m squared, m is in thousands of feet. Okay? These are the only variables that work in these formulas. I should say units. So let's look at a couple of quick examples, and I believe On the homework, what if you are solving for a meter? Let me back up real quick here. Right here, Josh, this first equation, this M, is the error in meters. And we have an example here on the next page. So calculate the error due to curvature and refraction. What is the error due to curvature and refraction in 2,500 feet? Well, we have feet, so let's go back and look. We can use this one, or we can convert our feet to miles if we wanted. So, going forward, there we go. 0.0206 times, remember M is in thousands of feet, so we have 2.5 thousands of feet squared. So the error due to curvature and refraction is essentially a little bit more than 1/10 of a foot, 0.13 feet. 400 feet, we're using the same formula, this time again 0.4 squared. So if we have to solve 2,500 meters, we have to convert it to feet or miles. No, you don't need to convert. Let's look down here at this equation here at the bottom. This equation, which is this one right here, is your error in meters. So if we have 1.8 kilometers, we can plug in 0.0675 times 1.8 squared gives us 0.219 meters. So we're off by 0.219 meters. If we have miles, we can use this formula, giving us, so over a distance of 2.7 miles, look how far off your measurement would be, 4.18 feet. That's huge, which is probably why a good reason why we don't measure using the level over a distance of 2.7 miles. We would break that up into much smaller distances, 400 feet, again less than 1,000 feet at a time, to make sure that our error correction is negligible. Josh, did I get your question answered? Does that make sense now that you would use this equation if you had meters? It looks like Josh is typing in. I'm just waiting a moment, so I don't want to miss the opportunity to answer his question. So, no, Josh, I think we're a little bit off there. Let's go back and take a look. This value right here, K, is in kilometers. So looking at your example, it would be 0.0675 times, if it was 2,500 meters, that's 2.5 kilometers, yes? Right? So let me grab my calculator here. Oh, okay, it says you got it. So 2.5 squared times 0.0675. So you would be off 0.422 meters. So almost half a meter, but not quite. Okay. I'm going to skip through all this, not as important. We've already seen the leveling rods. We saw those in lab. Trigonometric leveling. So what do you do when you come to, let's say, the edge of a cliff, right? Let's say you're carrying elevation and you're here. How do you determine the change in elevation from here to here? there's no way that you could read a rod that's tall enough like this, right? If your piece of equipment is set up here on top of the cliff, right? You need this horizontal line to be able to read the rod. There's no way you're going to have a rod several hundred or thousand feet tall, correct? So you're going to have to do something different, and that would be trigonometric leveling. And it's used when it's not feasible to use an actual level. And basically, I think we have a better picture here. Here we go. Remember that right triangle we keep learning about and hearing about, and I kind of keep harping on? Well, here's where this is put to use. So in this case, here's our point here at A, and here's our point here at B. And we're trying to figure out the difference in elevation between point A and point B. With our level, well, we're not going to use a level because a level can only measure on this horizontal line, right? Like right here. Well, clearly, we would have to keep putting a rod every few feet all the way up this hill, and that's not really an efficient use of time. So instead, we use another piece of equipment. We could use our total station, and you will have a lab very similar to this as well, that will allow you to determine this angle, this slope distance here, which allows you to create this right triangle. Now you can actually draw this right triangle, and I'm going to try to do this as neat as possible with this pen here. You can actually create this triangle in either direction, whether you're looking at it below or you're looking at it above. This H is this horizontal distance between the 2 points. You're measuring this slope distance, right, here. And then this angle and this angle are actually the same angle. And this angle is easy to measure with your equipment. So this is essentially what we've created, this right triangle here. We know from our trigonometric relationship that V, this vertical distance between the center of the instrument here and here, our rod reading, we know that that V right there is equal to the slope times the sine of this angle here. So we can calculate this entire distance there. Right? Here's the example I was talking about a minute ago where we're measuring off of the edge of a cliff of some kind, trigonometric leveling. This is the small HI that we were talking about earlier that I mentioned to not get confused with the capital HI. It represents the height of the center of the instrument from the point over which we're measuring. So if we know this elevation here at this point, 361.29, and we know that the height of our instrument is 4.72, and we know what V is, right? We can calculate V, right? V is going to be equal to the slope times the sine of our angle here, 30 degrees, 22 feet. Okay? Then we're able to calculate V. So if we know right here we're at an elevation of 361.29 and we're going up 4.72 feet, then the elevation right here is 361.29 plus 4.72. Seeing if I have this written down so I don't have to punch it in my calculator. That would have been good, but I don't. 361.29 plus 4.72. 366.01. So the elevation right here is 366.01 feet. We can calculate V. If you calculate V out, that I actually have written down here, that is 41.54 feet. So the distance from here to here is 41.54 feet. And we know here the distance from here to the ground is 4 feet. So if we subtract the 41.54 from the 366 minus 41.54, and then subtract this 4 feet here, we get 320.47. So 320.47 feet. That's the elevation of this point here. So we're carrying our elevation across using trigonometric leveling, using our trigonometric relationships to determine these variables. We could also determine the stationing. We know the station here. The stationing here would be this station plus the horizontal distance, which we could calculate also using our trigonometric relationships. So essentially, our change in elevation is going to be equal to the height of our instrument, small hi, minus v. Oh, the 30-degree angle is given in the problem. You're going to measure it in the field. You'd be measuring from horizontal down to where you're reading the rod. And so the 30 degrees, 22 minutes is measured. So our change in elevation between these 2 points is defined in this case as the height of the instrument minus v minus the rod. Okay. If we were measuring uphill, what would the relationship be? It would be the same if you were measuring uphill, except it would be plus v minus the rod. Okay? So your change in elevation with your trigonometric leveling is the height of the instrument plus or minus v minus the rod, depending upon whether you're going uphill or downhill. Okay, we've gone over some field procedures already. Again, this is just another image of what we've been continuously looking at. It's a single setup, so a single setup of the instrument, measuring from a point of known elevation, benchmark A, heading in this direction to get the elevation of point B. When we do this exercise in the field in a week, you're going to have multiple setups. So you're going to have a starting point of known elevation, and then you're going to carry that elevation to your next point, or you may need to set up a turning point. So we remember what a turning point is, right? It's just a temporary point, because clearly from here, if you drew this line straight across, you couldn't see this rod here. You'd be under the ground. So in order to carry our elevation across based on our direction of survey, we need to set up this temporary or turning point, calculate the elevation, and then move forward to get to either our next, in this case it shows as a benchmark, but you'd be getting to your next point of that you're trying to determine elevation. And then you would just pick up the instrument again and move forward. Oh, that's a really horrible arrowhead, isn't it? There we go. You would just be moving forward to your next point with your next rod. Okay, in your field notes, it's going to be important to describe the location and type of your first benchmark. All of your calculations should be done in the field book, and they should be checked and verified before leaving the site. It's important to note that the algebraic sum of all of your plus sites, which are your back sites, and all of your minus sites applied to the first elevation should give the last. That sounds very confusing, but let's just take a look. It basically means this is what a field book setup could look like. You have your stationing or your marks, right? Your initial benchmark, your temporary point, and then another benchmark in this case. You can see that they've given a description of each of the marks. The back site on that benchmark calculates, so we know the elevation of the benchmark. We add our back sight to get the height of our instrument. We then take our foresight on TP1 and subtract that to get the elevation of TP1. We add that back sight, because now we've picked up and moved the instrument, to get our new height of instrument. We take the foresight on our final benchmark, and it should match with what the actual benchmark is supposed to be. So we know that if we add our back sight and we add up our foresight, so here's the sum of the back sight, here's the sum of the foresights. If we take our initial elevation, right there, we add all of our back sights, we subtract all of our foresights, we should get our final elevation, whatever we calculated as our final elevation. If you don't, it means you have a math error somewhere on your page. Okay, we're going to skip through these for now. We don't need to go through all this. Oops. Okay, level loop adjustments. Essentially, it would be really nice if well, let me back up. When you do a leveling loop, you're doing just that. You're doing a loop. So you're going to start at a point of known elevation. You're going to collect all of your data all the way around, and you're going to come and check back in on that point of known elevation. That should mean that when you calculate that last elevation, it should be what it is, which is what you started with. So if you started out that this is 1,010 feet, when you come all the way back around, you know, you've had a point here, and you've had a point here, and one over here, and one here. When you calculate this last leg here, you should calculate to this elevation being 1,010 feet. In reality, you probably won't. And the amount that you're off is called the loop misclosure. There are certain levels of error that are acceptable when you do your loop misclosure, and you can calculate that error back out mathematically. If the error in the loop is unacceptable, it's too large, then you must repeat the entire leveling loop, or figure out which leg it is that you did incorrectly. In your textbook, they have you adjust elevation based on a proportional amount of distance between your points. I don't agree with this method, because when you do leveling and you're doing elevations, you don't typically find the distance between the 2 points. That's not common. So to adjust your elevations based on distance doesn't make a lot of sense. So the way that we will be adjusting them is by taking an average correction. This is the rule of thumb, the standard rule of thumb of precision for a leveling loop. It is just a rule of thumb. It's a good guideline. It's not always the end-all, be-all answer. It's going to depend on the purpose of the loop, the purpose of why you're out surveying elevations as to how precise you need to be. So to answer the question, how good is good enough? This is one way, a rule of thumb way to determine if you're good enough, but other surveys, they will tell you what your order of accuracy needs to be. So to calculate this, N here is your number of setups, which would be the number of times that you set up the instrument. And this calculated in is going to give you a correction. So let's say we had 6 setups. I'm punching in the calculator now. 6 times 0.02. So if n were equal to 6, then c is equal to 0.05 feet. So you shouldn't be off in your final calculation when you close your loop. Your loop misclosure should not be off by more than 0.05 or 0.05. If you are further off than 0.05, then technically you should figure out which leg was incorrect, or you need to go back and redo the loop. So we'll see how it goes in lab. in a week and figure out how close we are and whether or not we need to redo. But clearly, if you're off by half a foot or a foot in closing your loop, you need to go back and redo the loop. Okay? We are now at about 45 minutes in, and as I said, I want to keep these short to 45 to 60, no more than 60 minutes. So I want to ask now if anyone has any questions on this material. I don't know if any of you have started the homework yet, but the problems that you'll get at the end of the textbook chapter are very much tied to what you'll need to do in the field in terms of putting data into your field book and calculating data as you go. So it's good if you have that practice before you get to the field and you're trying to coordinate your readings and your recording and all of that. How do you find the stationing chainage of a lower station? Aha, let's go back. Excellent question, Josh. Let's go back here to our picture. Here we go. Oops, one too many. There we go. Here's the stationing right here. Actually, I'll put this in a different color so that, here we go. Here's the stationing there, 2 plus 7232 of this point. Oh, good. The stationing here is simply the horizontal distance between the 2 points. Right? Stations are always taken on a horizontal line. So we can calculate the distance between them by calculating this, h. And we know from our right triangle that in this case, h is going to be equal to s, which is our slope distance, times the cosine of 30 degrees and 22 minutes, right? Because again, the cosine of this angle is the adjacent side over the hypotenuse. So the adjacent side is h over the hypotenuse s, which if you rearrange the terms to solve for h is s times the cosine of this angle. That's going to give you a value. I don't know if I have that value already calculated. Let me see here, flipping back through my notes to see if it's here. No. So I'll go ahead and punch it in. Enter. So we have 82.18 times the cosine of 30 degrees, 22 minutes. All right, I get 70.91 feet. If somebody else wants to check me on that, that would be awesome. Oops, I'm sorry, 91 feet. Oh, okay, good. So our stationing here at our next point would be, I'm looking for a good place to write with this giant pen, 2 plus 7232 plus 70.91. So the stationing at our next point is 3 plus 4323. Does that make sense? Are we good on that? How did I get that? Okay. When we look at stationing, let's start with that. 0 plus 0, 0. This point right here would be 1 plus 0, 0, 2 plus 0, 0, 3 plus, oops, 0, 0. This thing isn't always the easiest to write with. Okay, so when we look at stationing, we're looking at a horizontal line of measurement. So if this is our 0 point, this would be 100 feet out, 200 feet out, 300 feet out. So in this previous example here, where'd it go? There it is. In this example here, you're located here at 2 plus 72, 32. So 2 plus, I don't know, somewhere about there. That's 2 plus 72.32. You're traveling a horizontal distance here, h, of 70.91 feet from this point here that we know, here, to get here, to this point down here at the bottom of the cliff. So we're traveling horizontally 70.91 feet as calculated, which puts us at 343.23. So if this right here would be 400 feet out, somewhere, I don't know, right about there, would be the 3 plus 43.23 feet. Does that make sense? We're just traveling along this horizontal line of stationing, and in surveying and on maps and all of that, they're always written as, you know, 1 plus 0, 0, which would be 100 feet, 2 plus 0, 0, 3 plus, 4 plus, as you go out. And then wherever your building fits or wherever your marks are along the way, they would be at uneven increments. So we went from here on our stationing at 272.32, a horizontal distance of 70.91, and ended up at a point 3 plus 43.23 along our stationing. Okay. Josh, did you get that? Does that make sense now? Okay, perfect. Are there any other questions or comments on this leveling or on the homework information that we need so far? Or are we good to wrap things up? Okay, I'm not seeing anybody jump up with, ooh, I have another question, I have another question. So I'm going to go ahead and stop the recording.